Hey everyone, and welcome to today's Explainer. We're going to take a pretty incredible journey today. We're going to start with the everyday microscopic static electricity you've likely experienced yourself, and we're going to drill all the way down into the invisible mathematical laws that literally govern our universe. Let's dive right in.
Here is our roadmap for today. We'll kick things off with the spark of static, then move into the rules of electric charge, mapping the electric field, the electric dipole, and finally, we'll wrap the whole shebang up with flux and Gauss's law.
All right, let's jump right into Section 1, the spark of static.
Now, to really wrap our heads around these concepts, we need to ground ourselves in a real-world scenario you can actually see and feel. You know, when you rub a balloon on your hair, or maybe you've rubbed a glass rod with a piece of silk and you get that weird, almost magnetic cling. We've all done it. But what is literally happening right there in your hands to create that static cling?
Well, it's all about electrons making a jump. When you rub that glass rod with a silk cloth, the glass actually becomes positively charged, and the silk becomes negative. Why? Because electrons are literally packing their bags and physically moving from the glass right onto the silk. But, and here's the wild part, if you grab a plastic rod and rub it with a woolen cloth, the exact opposite happens. The plastic actually steals electrons to pick up a negative charge, and the wool is left completely positive.
And so, this brings us to a fundamental definition: charging by friction. It's exactly what it sounds like. It is simply the process where rubbing two different materials together forces electrons to transfer from one to the other. You know, it seems like such a basic thing, right? Just rubbing stuff together. But this is actually the absolute bedrock for understanding how objects become electrically charged in our daily lives.
Okay, moving right along to Section 2, Rules of Electric Charge.
So now that we know how charges jump around on a macroscopic level, let's zoom in to learn the strict, unyielding rules they have to follow. Rule number 1, charges are additive. This just means that if you combine two charges together, their total is simply the sum of those parts. Got 6 coulombs? Add 4 coulombs, boom, you have 10 coulombs. In our big macro world, charges just add up to these large, seemingly continuous values. It feels like you can have literally any amount of charge you want.
But if we zoom way down to the atomic scale, the game completely changes. Down there, electric charge is what we call quantized. This means that charges only exist in very specific, discrete packets. No fractions allowed, ever. You can never have half a charge. Any observable charge in the entire universe is always going to be a neat, whole number integer multiple of one specific basic unit.
And what is that basic unit? It is exactly 1.6 times 10 to the negative 19th coulombs. That tiny, incredibly specific number is the exact charge of a single, solitary electron. Because of this whole quantization rule, you are never ever going to find a messy fraction like 2.3 times 10 to the negative 19th on a particle. It's impossible. This unfathomably small number represents the absolute, foundational building block of electricity. All right, zooming back out for Section 3, mapping the electric field.
So we have these individual electrons, but how do they actually interact across space? That's where the electric field comes in. What is it? Basically, it's the invisible region surrounding a charged object where another charge would actually feel a force. Picture this in your mind's eye for a second. Imagine you drop a tiny little test charge right next to a massive charged sphere. Even without touching, that little guy is going to feel a push or a pull. That invisible, ghostly force? Yeah, that is the electric field at work.
Now, we can actually map out this invisible field using electric field lines, and they follow some pretty strict rules. First off, they always point in the direction a positive test charge would naturally get pushed. Because of that, they always start at positive charges, and they always end at negative charges. And here's a huge one: they never, ever cross each other, not once. Why? Because at any single point in space, the electric field can only be pointing in one specific direction.
Okay, so how strong is this push or pull? We actually measure the strength of the field in a unit called newtons per coulomb. But here's the catch, and this is a super important detail. That measured strength actually decreases rapidly the further away you get from the source charge. Understanding this drop-off in strength is absolutely crucial for grasping how charges actually influence each other from afar.
Let's put some of these charges together in Section 4, the electric dipole.
All right, let's introduce a brand new configuration. What happens when we pair specific charges together in space? Let's break down the anatomy of a dipole. It's a surprisingly simple little setup, but man, it is the key to unlocking so much in physics and chemistry. Step 1. You take two charges that are exactly equal in size but opposite in sign.
So one positive, one negative. Step 2, you separate them by a fixed unchanging distance. That's it. That pairing creates your dipole. It has a specific direction, always flowing from the negative to the positive charge, and an overall magnitude that we call the dipole moment.
So what happens if you drop this dipole into a uniform electric field? Well, it experiences a torque, basically a twisting force. You calculate this by multiplying the dipole moment by the strength of the field. Because the two charges are opposites, the electric field pulls them in completely different directions. This literally twists the dipole, forcing it to try and align perfectly with those field lines.
And look, if you're wondering why we care about this outside of a textbook, here's why. The concept of the dipole is not just some abstract theory. As our source beautifully puts it, it explains the behavior of molecules like water. Think about that. Water itself is a natural electric dipole. This exact twisting, aligning torque we just talked about is exactly why water behaves the way it does, interacting with other molecules and electric fields. It's literally what makes life on Earth possible. Pretty wild, right?
All right, bring it all home with Section 5, Flux, and Gauss's Law. Okay, it's time to step fully into the 3D geometry of space. We need to talk about electric flux. Basically, flux is just a measurement of how much electric field is physically passing through a specific given area. Imagine holding a flat, square picture frame in the middle of a flowing electric field. The amount of flux catching inside that frame depends on 3 distinct variables: the overall strength of the field, the total area of your square frame, and the specific angle you're tilting it at relative to the field.
But what if we aren't dealing with a flat, open frame? What if we're talking about a completely closed, 3-dimensional shape, like a box or a balloon? Enter the incredible Gauss's Law. This is a real game changer. Gauss's Law tells us that the total electric flux blasting out of a closed surface depends solely and entirely on the electrical charge trapped inside of it. That's it. The external shape doesn't matter. The size doesn't matter. Only that internal and closed charge dictates the total flux.
To make this crystal clear, let's use the classic sphere example. If you take a charge and place it perfectly at the center of a sphere, the total flux bursting out through that sphere is directly proportional to that center charge. This law is just unbelievably powerful. It means we can take highly complex, messy electrical situations and solve them incredibly simply, just by focusing on the symmetry of the shape and the total charge enclosed within it.
So, we've come a long way today, right? From just rubbing a silk cloth on a piece of glass, all the way to uncovering the deep, mathematical symmetries of space. But it leaves me with this final thrilling question for you. If Gauss's law proves that invisible, geometric rules are firmly dictating the massive electrical forces of our universe, well, what other hidden rules are silently shaping the physical world around us right now? Food for thought. Keep asking questions, keep observing, and hey, thank you so much for joining me on today's Explainer.